Hello, class. This is Tim Tomlanovich. Hope you're doing well. This is statics. We're in Learning Plan 4, and we're going to learn about centroids and center of gravity, and then we're also going to calculate the area moments of inertia. Okay. All right. So for the calculating the centroids and center of gravity, we're going to locate the center of gravity of a body. We're going to calculate the location of a centroid of a simple area. We're going to calculate the location of the centroid of a composite area. Okay, so again, I made a lecture handout for you to fill in while you're watching this video, the key important things of the video. All right, so center of gravity versus centroids. Center of gravity, the resultant of individual gravity forces based upon individual weights of objects. So if I look at this, if you look over here, so we have rocks over here, okay? So they're all the center of gravity. So if I take a pen here, basically all the weights are, we find the center of gravity of the weight of each of these objects, and then they're going to balance. The same thing here, okay? It's based on weights. It's where I can put my finger and balance all that, okay? A centroid, so what we do in a centroid is we assume an object is homogeneous and in uniform thickness. So typically in construction building materials, that is the case. A wood 2x4, we can assume that material is homogeneous and the thickness is the same, which is typically the case. Same with steel, concrete, okay? So instead of basing our calculations on weights, we're going to calculation our areas on, or our areas, okay? So if we can assume that the material is homogeneous and uniform thickness, center of gravity will equal the centroid, okay? Okay, so here's over here, so we have a little picture of a centroid, right? So we basically find the centroid of the area of that triangle, okay? All right, so how do we find the center of gravity? Okay, X bar, so here's our formulas. X bar equals the sum of the individual weights. So I'm looking at the top term here. Sum of the individual weights times the distance from the point of origin to the individual centroid divided by the sum of the individual weights. Okay. Y bar is the sum of the individual weights times the distance in the y direction to the individual centroid in the y direction divided by some of the individual weights. Okay. All right. So this will make sense when we do an example. So X bar, distance to composite y-axis center of gravity from the point of origin measured parallel to the axis. Okay, so we are measuring in the, when it's X bar, we're measuring in the X direction. So the X bar actually locates the Y centroidal axis. Y bar locates the XX centroidal axis. Okay. So Y bar is distance to composite. So when I say composite, that means it's the entire object. When I say component, that means what we do is we can break that object up into individual components like triangles, circles, rectangles, because we know where the center of gravity of those are. Okay. So distance of composite XX center of gravity from the point of origin measured parallel to the y-axis. Okay. W equals the weight of individual components. X equals distance from point of origin to the y-axis center of gravity of the individual component. There's that component. And y is the distance from the point of origin to the x-axis center of gravity of individual component. Okay, so this is how we calculate the center of gravity. So if you look at table 3 in your textbook, as you can see, the center of gravity of a rectangle we know is halfway okay? B over 2, so my distance B here, okay? And then my distance h over 2, my distance h will locate the y and the x centroidal axis, okay? Here's how I calculate the area, okay? So now what I want you to okay? So if you look at a triangle, so is number a triangle, if I draw a triangle here, so this one's kind of confusing, but it's a right triangle. So what we like to do is make right triangles. So I know this distance from here to here is 1/3 h, and the distance from here to here is 1/3 b. If I make b this axis and h that axis, okay? That's we just know that. In circles, the center of gravity is right in the middle there, okay? So if you ever wonder how to find that out, you can look there. So here's a half circle, circles, rectangles, radiuses, okay? So you're going to be using this table in your book quite a bit. All right, so let's do our first example. So this is center of gravity example 1, problem 7.4 on page 152. So I'll read out the problem to you and we'll go work on it, okay? All right. 7.4 on page 1, a solid steel shaft is fabricated as shown. Locate the center of gravity with respect to the left end. Okay, so basically, where am I going to put my finger to balance this? So I'm trying to find the center of gravity, the y centroidal axis. Where is that? So basically, what I need to do is so do this. So this is y. So I'm going to start from an origin here. Okay. And then what I want to find is the problem is asking me what is x bar. Okay. So basically what we do is we break this up into components. Okay. So I'm going to make a little spreadsheet here. So I'm going to call this component, a table. Okay. We're going to call this component 1, component 2, component 3. Okay. So we know this is a rectangle. So we know the centroid in the x direction is right there. Centroid in the x direction is about right there, and the centroid in the x direction is right about there. So if I start from here to here, if this thing is 6 inches long, we know it's b over 2, so it's 3 inches. And then from here to here is 4 inches, and then from here to here is 2 inches. Okay, so component 1. Okay, so this is a solid steel shaft. Okay. All right, so what we need to do is figure out the weight. Okay. So how much does steel weigh? That is a good question. Okay, steel, so we need a density, right? It's 490 pounds per cubic foot, PCF, pounds per cubic foot. It is a steel shaft, okay? So how do we calculate the volume of a cylinder? Okay, so we know it's a 5-inch diameter. Oops, didn't mean to do that. Let's go back into here. So we know pi d squared, okay, will give me my area, which equals area, all right? And then we take our area times our length will give me my volume times my weight will give me my weight per cubic foot, because this will be pounds per cubic foot, okay? So, all right, so pi for component 1, and I'm going to make this nice and neat on the next page. Pi times what do we got here? Diameter is 5. Pi d, I'm sorry, it's pi d squared over 4. Over 4 equals, so if I take my calculator, all right, shift, I got to find my pi key here. They always like to hide. I have 3 different calculators, and every calculator, it's in a different spot. So, well, as soon as I find it, I'll let you know. There it is. Pi times 5 squared divided by 4. So I get 19.63 square inches. Okay. Times 6 inches long, right? Okay. So 19.63 times 6. So I get 117.78 cubic inches is my volume of my sphere. Okay. So 117.78 cubic inches times, all right, so we know the weight of steel was, we look here, 490 pounds per cubic foot. Times 490 pounds per cubic foot. However, if I look here, I have cubic inches here and cubic feet here. So I need to convert this into cubic inches. So 1 cubic foot, right? These cancel out now, equals 1728 cubic inches. How do I figure that out? I take 12 times 12 times 12. 1,000, okay? All right. So 117.78 cubic inches times 490 divided by 1728. That equals 33.4 pounds. Okay. So pounds per, right? So the cubic inches cancel out. Now we're left with pounds. So 33.4 pounds. Okay. So I'm going to make this nice table on the next sheet here. Okay. Component 1, weight. So if I look back, 33.4 pounds. Okay. Component 2, all right, we have 3-inch diameter cylinder. So same process, except instead of a 5 here, I'm going to put a 3 here and go through the same process. So I'm not going to write that out. All right. So pi times 3 squared divided by 4. So I get 7.068 square inches times 3-inch times 8 inches long times 8 equals times 490 equals divided by 17. So I get 16.0 pounds for component 2. Component 2 number is this guy right here. 16.0 pounds. Okay. Component 3, all right, is 1-inch diameter. So 1 squared times pi divided by 4 equals, my length is 4 inches times 4 times 490 divided by 1728. I get 0.89 pounds. Okay, so I had the weights of each components. Now I need to find X, and that's in inches. So X is the distance from the point of origin, which we always like to start in the lower left-hand corner if possible, because then all our numbers are positive because we're going to the right, to the individual component. So component 1, component 2, component 3, centroid. I'm always measuring back from the point of origin. So this is 0, 0. So if I go like that, I get 3 inches, right? Would you agree? From here to here is 3 inches. Okay. 3. Component 2 is from here. Remember, don't go from here to here. You got to go all the way back from here. So we go 6 plus 4 is 7. Okay. And then component 3 is here. So we go 6 plus 8 is 14 plus 2, right? Half of that. So 6 plus 4, or 6 plus 8 is 14 plus 2 is 16 inches, all the way back from the point of origin. So I do believe, what did I say, 16 inches? Okay. Sum that up. So now we're going to take our weight times x. Because if I look at my formula, what does this say? Weight times x. Weight times my x distance, okay? So what I'm doing, so now that's what that column is, but I need to know the sum of my weights. So 33.4 plus 16 plus 0.89. So 50.29 pounds. So that's the sum of my weights. Okay. So now I'm going to take 33.4 times 3. That's a 100.2. Okay. 16 times 7. That's 112.0. And then 0.89 times 16. That's 14.24. Okay. Now I want to sum this up too, right? 100.2 plus 112.0 plus 14.24. 226.44. Okay? So now we know x bar equals the sum of W, the weights times the individual component distances over the sum of the weights. Okay? So we have 226.44 divided by 50.29. Okay? 226.44 divided by 50.29. And that equals 4.5 inches. So that is telling me I can put my finger at 4.5 inches from 0, 0. So let's do that in red. So this is 6. Okay. That's where I'd put my finger, and that will be my y, see? My y centroidal axis. So that's in the distance in the x direction of where I need to put my finger, and I will be able to balance that. It kind of makes sense, right? Because this is a big area. This 5-inch diameter is big, so it's going to want to, so that's where I can put my finger, and this thing would be balanced, okay? Why is this important? Okay, because if our loads are not on the centroidal or center of gravity axis, we create a moment and it starts bending and shearing. And we'll talk about that more later. Okay, so that's how I find the center of gravity. So X bar. So if I wanted to find it in the y direction, I would do the exact same process. However, if you look, this is symmetrical. This is in the middle of each thing, okay? But I do the exact same process, except instead of x, we'd find y, and it'd be y times x, and then I can use the y formula, okay? All right, so this is another table you're going to be using quite frequently. All right, so let's talk about centroid. So if you look at these formulas, the centroid, instead of the W, as we see right here, it's an area. A stands for the individual component area. So we need to find the centroid in the XX centroidal axis, which is Y bar, okay, and the YY centroidal axis, which is X bar, because we need to know where the centroid of that composite section is. Because if our load does not go on that and on the centroid, we will create a moment. Okay, and we all know what a moment is. It's a force times a perpendicular distance. Okay, so this is why it's important that we do design that we know where this is. Okay, so basically everything is exactly the same because y is we are assuming the material is homogeneous and it's in uniform thickness, which is true and typically true in building materials. Okay. All right. So let's go right into the example. All right, centroid. So this is problem 10.7.1c on page 153. Okay, so all right, so the says locate the centroid of the area shown in part B. Note the symbols signifying that the area is symmetric about the center line. Okay. All right. So what we first need to do, let's create a little table here. All right. We're going to create a table here. So we're going to call it component. Because what we want to do with these, we want to break it up into known shapes. Okay. So so basically we have a hole here and we have a circle here. Okay. So when you have a hole in an object, you're going to subtract that, okay, from your centroid because it's not there, it's air, okay? So what I'm going to do is I'm going to make one big box, and that's going to be called component 1. So I know that box is 9 by 8, right? Okay. So component 1 is 9 by 8, okay? Component 2, okay, as I'm going to make this little box here, right here, which is 3 by 3. Okay. Component 2 is the little box, which is 3 by 3. And what I'm going to do is I'm going to put a negative by it because it's a hole. That means we need to subtract it out of our equations. Okay. And then component 3 is the little circle. Okay. Component 3 is the circle. Okay. And then it is, what's our diameter? 4-inch diameter. Okay. Okay. All right. So now that we broke it up, and again, this is a hole, so we want to subtract that, right? All right. So our next column is we want to find the area of each of these individual components, component 1, component 2, component 3. And that is its area is inches square. So 9 times 8 is 72 square inches, right? 3 times 3 is 9. Now, remember that little 3 by 3 area is air, okay? Remember that. This is air. This little 3x3 area here is air. Okay, so this is component 2, component 3, and component 1 is the big circle. Okay, it's air. So we want to subtract that. Okay. All right. So and then pi d squared over 4, or pi r squared, same thing. So 4 squared times pi divided by 4 equals 12.57. So that's also a whole. So we want to subtract that, 12.75 square inches. All right, now we want to sum these up. Okay, so we go 72 minus 9 minus 12.57. That's 50.43 inches squared. Okay, all right. So now what we want to do is find our x distance. Remember the x distance, and that's in inches. Okay, that is the distance from the point of origin to the individual component centroid, the individual YY component centroid. Okay, so let's go back to our diagram. Point of origin, where are we going to make our point of origin? We're going to make that right here. Okay, right here. This is our 0, 0 mark. Right there is 0, 0. Okay, now, so component 1, we know it is a, so we're measuring x. So when I look at my table here, it's x, so I'm measuring in the x distance. All right, so I look at my table. X, so halfway to the square as a whole, I'm ignoring all the other shapes, right? I'm just pretending it's a big solid block. I know it's 4.5 inches. Okay, so I'm going to go blue here. 4.5. Okay, now component 2, I know here's 0, 0, so I know it's 3 inches. So in the middle of a box, I know in the middle of a rectangle, it's halfway, so it's 1.5 inches from 0, 0. So 1.5. Okay, and then what do we got here? So we got our circle. So we know it's 4 inches from this end, so that means it's 5 from this end. Because, right, 9, we always want to measure from 0, 0. 5 to here plus 4 will give me 9, so it's 5. Okay, now we're going to take our individual areas and multiply it by our distance, and that'll be inches cubed. So I take 72 times 4.5, and that's 324. Okay, so now we take 9 times 1.5. Remember that 9 is negative, so that's a negative 13.5. Okay, then we take 12.57 negative times 5. That's 62.85, a negative 62.85. Now I want to add those up. Okay, 324 minus 13.5 minus 62.85. Okay, so that's 247.65. Okay, so now what we find, we're going to find y in inches. Okay, so component 1. So I'm going to do the y, let's do that in black so we have different color. All right, so component 1 is the big 9x8 square. Remember, I'm assuming it's a solid block, so measuring from 0, 0. I know the centroid of the 9x8 square, so I'm measuring in the y direction because I'm looking for y is 4, because I know it's 8 inches from 0, 0 up. So my first number is 4. Okay. Now I gotta start subtracting the holes out of the things, right? All right. So from 0, 0, so we go 5 plus 1.5 is 6.5. So this is 6.5. Okay. And then the circle is, we know it's the centroid is in there. Where can I find these? Remember, look at the charts in your book. So we know it's 3 inches there. Okay, so now we're going to take A times Y, and that'll be inches cubed. So we take the area, again, 72 times 4, that's 288. Okay, we take a negative 9 times 6.5, that's negative 8.5. Then we take a negative 12.57, number to A is the area, times 3, and that's negative 37.1, or 37.71. All right, I'm going to sum all these up. Okay. So 288, now I'm subtracting the holes out. 0.5, whoops, let me clear out here. 288 minus 58.5 minus 37.71. That equals 191.79. Oops, I did it again. Gee, sorry about that. 191.79. Okay. All right. So now going back, if I go back to my equations, sum of the areas times the x distances, I have them all summed up in my table here. So now I can find x bar and y bar. Okay. All right. So let's do that in red. Okay. X bar equals the sum of the areas over sum of the area. So we have 247.65 divided by 50.43, and that equals 247.65 divided by 50.43, 4.91 inches to the right of 0, 0 inches. Okay? All right, and then y bar, okay, y bar locates the x-axis centroidal axis from the point of origin. The composite, so we're trying to find the composite centroidal axis, is the sum of the areas times the y distances divided by the sum of the areas. So we have 191.79, I'm looking right here, divided by 50.43. So 191.79 divided by 50.43, and that is 3.80 inches. Okay. All right, I just located the centroidal axis, so let's put that up there, x bar. All right, so I'm going to use blue, and we'll make this nice and thick. Okay. All right, so we know our x bar is 4.91 inches. So that's almost 5. So, or our x bar. So our YY centroidal axis, okay, and then from 0 is 4.91 inches. Okay. All right. So x bar, remember, locates the YY centroidal axis. All right. Y bar is 3.8 inches. So that's 3. So it's right about there. So this is X, X, okay, Y bar, okay, and that equals 3.80 inches. So right there basically is where the centroidal axis. So if as long as my point loads hit right there, I will not create a moment on this shape. But as soon as if I get a moment acting anywhere away from the centroid, I'm going to create a moment and bending stresses in this shape. Okay? So that's why we need to find that. So that's how we calculate the centroid. Okay? All right. So your homework for centroid is read chapter 7, go through the examples, make sure you understand the examples. Problem 7.1, 7.3, here's your homework. Okay, remember there's a solutions manual in there. Try to go through the homework problems without looking at the solutions. Then you know you've spent enough time. If you can repeat your answer several times without looking at your notes. Okay. All right. So now we're going to move into moment of inertia. And I'm going to take just a little quick. All right. Moment of inertia. So describe the area moment of inertia. Okay. So what is the moment of inertia? So that's what we're going to find out. And I'm going to tell you why this is important in statics and structural engineering. Calculate the moment of inertia of simple shapes about the centroidal axis. Again, calculate the moment of inertia of simple shapes about the centroidal axis. See that? So this is why I had to tell you how to find centroidal axes, because you need to find the moment of inertia. Calculate the moment of inertia of simple shape about a non-centroidal axis using the transfer formula, and then calculate the moment of inertia of a composite area. Okay, so this is what we're going to learn in this area moment of inertia. So what is the area moment of inertia? It is a mathematical value describing the stiffness of a structural member. Okay, so I like this example right here on the right side. So you always wonder, why do we put floor joists upright? So if I look here, okay, if I look here, if I find my centroidal axis, I didn't quite hit there. So this is XX, this is Y, Y, right? So now if I just rotate this board over here, okay, this is Y, Y. So, okay, so basically this Y and this Y are equivalent. Okay, I just rotated the board. So you notice, so if I look here, the load from this gentleman is what? Is wanting to rotate it around the x-axis, right? Now, the load here, when I flip the board over, wants to rotate it around the y-axis, okay? So, why is it bending? Okay, so if I look here, this is perpendicular, this is perpendicular, okay? So there is called a stiffness of a structural member. So it's mathematical value. So basically, the higher the number, the more stiff it is, okay? So why is this important? So basically, by trial and error, way back when building started in the 1800s, we've realized that, oh, when I cut my board out, right, if I stand it up long, I get less deflection here. I get less deflection, right? It's stiffer when my load is acting in the XX centroid against rotating around the XX centroidal axis. But when I lay it flat, basically I lay it flat, and I put my load against the YY centroidal axis, I get more bending. Okay, so by knowing that, I know my moment inertia about the XX centroidal axis is stiffer than the moment inertia about the YY centroidal axis. Okay, so these are actually two different numbers. So we're going to pick the bigger number. Okay, so when you look at a steel shape right here, all right, x, x, y, y. So which way do you think is stiffer? Okay, so if I put a load anywhere, basically rotating it around the x-axis or loading it this way around the y-axis, rotating it around the y-axis, most likely it's going to be stiffer around the x-axis. Okay? So this is why we need to find the centroidal axis. So literally it's a mathematical number and it's inches to the fourth. That doesn't mean we're in four dimensions. Okay? So that's what the area moment of inertia is. Okay? So if I look at these tables again, if I look right here, it says moment inertia I. Okay? So I want you to notice something. All right? Is you see IXO, IYO. That signifies the moment inertia about the centroidal axis, the composite centroidal axis, or the individual components centroidal axis. Okay? You do not want to use this one. This is more advanced, and I'm not going to even discuss that. Okay? So so if you look at a circle, right? So if you look at a circular pile, right? You notice something? IXO equals IYO. So the moment of inertia along rotating around the x-axis is equal to the moment of inertia rotated around the y-axis. It's the same answer. And it kind of makes sense because it's symmetrical. And this is why we like to use square posts too. Okay? So if I come up here, if you look here, in the formula, BH cubed, HB cubed. So see that these terms are turned around, but if B and H are the same, right? If it's square, that means we don't have to worry about which way is which is our stiffer axis. So a real life example of this is we actually had to put piles into a circular foundation driven to bedrock. Okay, so this is, okay, we were putting piles in. Some went this way, some went that way. Okay, so when I look at that, when I look at loads, so I could have wind loads. It was a silo. I don't know which way my load is going to come. Okay, so if I look at the strong axis, that's this way, right? Okay, that's the x centroidal axis. That's my strong axis. Okay, so the structural engineer asked me, well, don't we need to orientate the piles a certain way? Because there's a strong, weak axis and a strong axis. I said, yes, you are correct. However, when I did, it's called an L pile analysis to figure how big this steel I-beam had to be. I assumed my moment of inertia was the value I used for my design was along rotating on the YY centroidal axis, which was the weak axis. So it did not matter which way piles were rotated, which was great. Okay. Granted, I needed more piles because I have, less stiff, but it eliminated a lot of confusion. So that's kind of where this comes into play. Okay. So here's again moment of inertia. All right. So transfer formula or the parallel axis theorem. So basically, first thing I do is I find the composite centroidal axis, okay, and then any shapes that do not fall in the composite centroidal axis actually increases the area moment of inertia. Believe it or not, it makes it stiffer. So is everybody? So if you think about this, oops, just let me. So everybody knows a typical joist looks like this. Okay, so then all of a sudden they came up with these little eye joists. Okay. Same height. Okay. If I look at my composite, believe it or not, by just doing this and making this, because the centroid here and the centroid of this here is actually increasing the moment inertia. It's making it stiffer. Counterintuitive, isn't it? So it's very interesting. So I'm taking material away, but I'm actually making this stiffer because I have an object that's away from the composite centroid. I have an area that's away from the composite centroid, and it's actually adding to the moment inertia when I put a load against this. So this is why these eye joists and things come. So believe it or not, it's a very interesting thing. So transfer formula: I is the composite area, moment inertia. I naught, or I is 0, individual component centroid. So if I look here, I have 1, 2, 3. Here I have 1. So here's individual composite centroids. So I have 3 objects here. A, individual component area. So I figure out the area of each moment. And D is the perpendicular distance between the parallel axes. Okay, so basically here's my individual component centroid. I have a distance here, and a distance here. So if you look at, you're taking the moment of inertias and you're adding the area times the distance squared. So it's making the moment inertia bigger. It actually helps it versus just the square shape. Okay, so that is called the transfer formula. All right. So typically what we need to do to make things stiffer is, one is we make it narrower and slender and higher, or we just make weird shapes. Okay. So let's get right into an example. Okay. So this is problem 8.9c on page 173. So now we're in the chapter 8. All right, so basically what it's asking us for is calculate the moments of inertia with respect to both centroidal axes for the areas shown. Okay, all right. So the first thing we want to do, so first step in this, because this is a composite centroid, so we have an area 1, okay, and we have an area 2, okay? All right, so what I'm going to do, so we can, the first thing what you can do is it symmetrical? It is. So basically, if I put the YY right down the middle, I don't have to find my X bar. But to make life interesting, I'm going to put everything starting right here at 0, 0. Okay? So step 1 is, first we got to identify the components. Okay? And then we got to find the composite centroid location and the XX and YY. Okay? So I'm going to start making my spreadsheet here. So component, because you're going to see a lot of these values end up being the same. Okay. So component 1 is this guy, right? So how big is that guy? So it's 8 by 2, right? Because I got to subtract 2 inches. So 8 inches by 2. And then component 2 is what? 6 plus 2 plus 6. So 12 plus 2 is 14 by 2. 14, 2. Okay. We need the area, right? Area. Okay. All right. So same thing. If there was a hole in there, I would subtract the area out to find the composite centroid and the moment inertia. Does it make sense why you would subtract it out in the moment inertia? So when I cut a hole in something, doesn't it make it weaker? Yes. Okay. So area 1. of component 1 is 16 square inches. Remember, okay. Area 2 is 14 times 2, which is 28. Okay, we need to find the sum of that. So 16 plus 28 equals 44. Okay, so x, remember that's from 0, 0 to the individual component centroid. So we're 60 here, plus this is 2, so 1. So 1, okay, remember I'm breaking this up into 2 different objects. Okay, I'm looking at each individually from 0.00. So I go to 6 plus, this thing is 2-inch wide, so rectangle is 1. So this is 7. Okay, and then this one is 6 plus 1 is also 7. Okay, and then I do area times x, and that'll be inches to the third. So I take 16 times 7, that's 112. We take 28 times 7, that's 196. Okay, I want to sum that up. Plus 112, that's 308. Okay, now I want to find my y distance. All right, from 0, 0 to component 1. All right, so I know it's 10 from here to here, right? Did I just goof up? This is actually 12, so this is actually 10 inches. So we are going to hit the eraser button, and we made a mistake there. Okay, it's 10 from here to here, so 10 times 2 is 20. 20 times 7 is 140. Okay, sorry about that. So it's 5 plus 2 is 7. So that's or I'm sorry, 6 plus 1 is 7, right? And then the y is 2 plus 5 is 7. Okay. All right. So now we're back at it. So 140 plus 196, that's 336. Sorry about that. All right. So y distance to component 1. 7. Yes. All right. Y. 2 plus 5 is 7, so 7 again. Right? And then this one is 1. Okay. Just going to double check here. So 7 and 7. Yep. Okay. Oops. So let's go area times the y distance. So 20 times 7 again is 140. And then 28 times 1 is 28. Remember, I'm always measuring from the origin. So 140 plus 28 equals 168. All right. X bar. Okay. Remember, this is X bar equals sum of the areas times X distances divided by sum of the areas. Okay. So this is area times X right here. So that's 336 divided by my area is 44. 336 minus 44 equals, oops, 336 divided by 44. That's 7.63 inches. Okay. Is that right? Did I do that right? 6 plus 7. 336 divided by 40. Oh, this is 48. That's why. 10 times 2 is 20. That's 48. 336 divided by 48. 7 inches. All right? So we knew it was going to be 7 inches, right? Because it was symmetrical. So you do not have to do that unless I tell you to go from 0, 0. Okay? Y bar equals sum of the areas times the y distances divided by sum of the areas. All right, so we have 168 divided by 48. That's 3.5 inches. Okay. All right, so we know y bar or x bar is 3.5 inches. Okay. All right, so now if we look at the individual component centroid, so this guy is 5 inches. So that's sitting right about there. Oops. Okay. And this guy is sitting right about there. Okay. So if I look here, especially around the, I have a distance dy, okay? And then I have a distance here, dy2, this is dy1, component 1, okay? However, I do not have a distance, okay, away in the x direction away from the y centroidal axis. So basically what that's going to do is going to help us with our moment of inertia. So this is the transfer formula. All right, so now we can find the moment of inertia. We located a composite centroid from 0, 0. Okay, so we're going to continue this table because we're going to use the same information. Okay, so I'm going to make this more clear here. So this was 48 inches squared. Okay, all right, so now what we need to find, I'm continuing on the table. I need to find the individual, let's use green, individual moment of inertia along the x component, okay? In the x direction, all right? So x, y, okay? Where do I find that again? Right here in our tables. So IXO, individual, is BH cubed over 12. Okay. So BH cubed over 12. So B, right? B is this way. So remember, just keep it orientated the same as the diagram here. B is the horizontal distance, H is the vertical distance. Okay. So component 1, B is 2, and Y and H is 10. Come on. So 2 times 10 cubed divided by 12 equals, okay, so this is component 1. So 2 times 10 cubed divided by 12, and that equals 166.67. So this is component 1. Component 2 is the same formula, right? All right, so our B is 14, See, I can look right here. 14 and our H is 2. Okay. So B is 14. Our H is 2 times 2 cubed divided by 12. Okay. So 14 times 2 cubed divided by 12, and that equals 9.33. So as you can see there, that's a pretty small moment of inertia. Okay. So I want to add these up. So 166.67 minus 9.33. Oops, I don't want to. I want to add them. 0.67 plus 9.33. That equals 176 inches to the fourth. Now, if I had a hole in there, I would actually find the moment of inertia like pretending it's a solid object, but I would subtract it. Okay. All right. So now we want to find D. What do we want to? Okay. So we want to find dx. Dx. So we want to find a distance because number x is measured in the x direction. Okay. Distance. So we want to find the x distance, dx. Okay. So as we know, this is 0. This is 0. Okay. So our next column is area times our distance in the x direction squared. So 0, 0. Okay. So this is the parallel axis theorem. Is there a centroid that is not an individual component centroid, not on the composite centroid? And if I look at my diagram, there is not. Okay. Because the individual component centroid is what? 1 inch in here, and we got 7 here. So I go 6 plus 1, it falls right on there. This one here, same thing. Okay, it's on there. So there is no parallel axis theorem. There's nothing that's acting in the x direction. Okay, so you take the area times that distance squared. So any number times 0 is 0. Okay, so that's where we get that. So we sum this up, we get 0. All right, so now let's find our moment of inertia in the y direction. Okay, so component 1. All right, so if I look here, back in here, IY0 is H and B got switched around here. H and B got switched around, okay? So here's the formula here. H and B get switched around, okay? But the orientation doesn't change. So B is still 2 and H is still 10, but the formula gets switched around. So it is HB cubed over 12, okay? So this one is 10 times 2 cubed divided by 12 for component 1. And then this is 2 times 14 cubed divided by 12. Okay? Because my H is first and now my B is second. So B, okay? So what do I get there? All right. So 10 times 2 cubed equals, divided by 12, that equals 6.67. Okay. Sorry, that's a cubed up there. All right, so now I do the next one. 2 times 14 cubed divided by 12, 457.33. So there we go. 457.33. Okay. All right, I'm going to add these up. So 6.67 plus 457.33 is 464 inches to the fourth. So that is the summation of the individual component moments of inertia. Okay, so now we want to find that y distance, dy. Okay, so let's go back up to our picture, our diagram. All right, so component one, there is a distance from here to here, right? Because it's the dy is the distance in the y direction from the, so if you remember, this is the individual x component centroid. So it's the distance between the individual XX centroid and the composite XX centroid, okay? See, these two lines are parallel, so it's that distance in between. So we need to figure that out, okay? So we know it's 5 to there, okay? All right, and then, so how do we, so we need to get this distance right here. So how do we do that, okay? So that distance is what? So if we know it's 3.5 to there, okay, and then we know, from 0, 0, if I measure from 0, 0, if it's 3.5 to there, and then from there to there is what? Is 7. So 7 minus 3.5 will give me that number. And that is 3.5. So we have a dy for component 1 is 3.5. So this is 3.5. Okay, let's do component 2. All right. All right. So we know it's 3.5 to there, and we know it's 1 to there. So 3.5 minus 1 will give me this distance. So if I'm always measuring from that 0, 0 mark, it makes it easy. 3.5 minus 1, right? Because this is this centroidal individual. So dy2 is 2.5. Okay. So this is 2.5. So this is inches. Whoops, this inches. Okay, so now we're going to take the area times the distance in the y direction, and I'm going to square the distance. And that'll be our added moment of inertia. Okay, so we take Iy is, so area. So we got to go find our area, which was in this sheet, which is 20. 20 times, so the area of component 1 times the distance, which is 3.5. 3.5 squared equals, so 245. I'm adding a moment of inertia of 245 inches to the fourth. Okay, the area of component 2 is 28. 28 times that distance squared, just the distance is squared, is 175 inches to the fourth. Okay, so I'm going to add those up. That equals 420 inches to the fourth. All right, so final answers. I rotated in the x direction is the sum of the individual moment inertias, okay, which equals IXO plus area times dx squared, which equals, so here's my sum, see IXO right here, the individual component centroids, which equals 176 inches to the fourth, plus the summation, sorry here, I got to put some signs in there, of my distance plus 0 inches to the fourth. So that equals 176 inches to the fourth, which equals I x. I is the composite moment of inertia. Okay? The composite moment of inertia in the y direction equals sum of the moment inertias in the y direction of the individual components plus the sum of the areas times d, the distance in the y direction squared, which equals, so here's 464. That's the sum of the individual component moment inertias plus my distance plus 420 inches to the fourth. That equals 464 plus 420 equals 884 inches to the fourth, which equals the composite moment inertia in the y direction. So, which direction is stiffer? Okay, so this is x, x. This is y, y. Okay, so according to this, my load, this object is actually stiffer, okay, going around the y-axis. Okay, so if I go here and so basically it's telling me that if I put a load this way, it's going to be and rotate around the y-axis, it's not going to deform much as going this way around the x-axis. Okay, so believe it or not, you would think that you would want to put it that way, but it's actually that way. Okay. I have to think about something. I think I made a huge mistake for you guys. Because something does not seem sense here. dy. Okay, I am going to have to state something here. I think I got my numbers backwards here. I think this should be dy, and that should be dx. Maybe not. I think we're okay. I will confirm. I will confirm. Okay. All right. So here's your homework for Chapter 8. Let me confirm this example. I'll throw out another one. What I'm going to do is I'm actually going to do these examples on engineering paper so it's nice and neat for you guys, and I'll scan it and put it in there. Okay. That way I can confirm this, and this will be nice and neat for you so you can follow my work better. Okay. So with that, that is the end of this lecture. So